The DeepCell system is a provider-side fingerprinting localization system designed to provide high-accuracy localization for any cell phone. It leverages unlabeled cellular measurements recorded by the cellular provider and opportunistically synchronizes with selected client devices to get location labels. The fingerprint is then used to train a deep neural network model for localization. The system addresses challenges such as using unlabeled data, handling noise and sparsity, scaling data to large areas, and providing enough data for training deep models without overhead. Evaluation shows a consistent median accuracy of 29 meters, outperforming state-of-the-art client-based systems by more than 75.4%. This accuracy is extended to low-end phones as well. The limitations of current localization systems, including GPS and Wi-Fi-based systems, are discussed. These systems are not available in low-end phones, highlighting the need for a ubiquitous localization system that can work with virtually zero extra power. The paper introduces DeepCell, a provider-side fingerprinting localization system that leverages unlabeled cellular data to build a fingerprint. DeepCell trains a deep model to capture the unique signatures of cell towers at different locations. The system is designed to achieve high-accuracy localization without additional energy consumption. The evaluation of DeepCell shows a median localization error of 29 meters, outperforming state-of-the-art techniques by 75.4%. The system's architecture is described, including its offline training and online tracking phases. DeepCell is a ubiquitous, accurate provider-side cellular-based localization system that leverages deep learning techniques to enhance the precision of user location estimation. The system's architecture consists of several modules, including the offline spatial augmenter, grid generator, model trainer, data collector, and grid estimator. The offline spatial augmenter module handles noise and sparsity in the training data by predicting unknown cellular measurements for new locations, thereby increasing the number of training samples. The grid generator module superimposes a virtual grid over the area of interest and uses geotagged cellular measurements to construct the deep model for each cell. The model trainer module trains a deep neural network model using labeled cellular measurements records associated with grid information. The input to the model is cellular measurements from different cell towers, and the output is a probability distribution over the different grid cells in the area of interest. During the online tracking phase, a user's location is estimated by fetching cellular measurements and forwarding them to the grid estimator module. The grid estimator module uses the trained deep network to calculate the probability distribution of each grid cell and fuses this information using the fine estimator module to estimate the final user location. DeepCell addresses various practical challenges, such as building the fingerprint from provider in labeled cellular data without overhead, handling noise and sparsity in provider data, scaling the data to large areas, providing enough data for training deep models without overhead, training the deep model while avoiding overtraining, and increasing model robustness. The data synchronizer module plays a pivotal role in aligning GPS location labels from the traces database with cellular measurements records from the provider's unlabeled database. This process involves converting phone timestamps to GMT and considering a match if the time difference is less than 10 ms. Following this synchronization, the spatial augmenter module significantly increases the number of training samples by predicting unknown fingerprint values using a Gaussian process. This process effectively captures the relationship between cellular measurements and location labels, enhancing the dataset's robustness. Next, the grid generator divides the area of interest into a virtual grid, mapping each sample to specific cells for training purposes. This step is crucial for organizing the data in a manner that facilitates efficient model training. Finally, the model trainer module utilizes the spatially augmented fingerprint samples dataset to train a deep neural network. This advanced model leverages the enriched dataset to learn complex patterns and relationships, ultimately improving its ability to predict locations based on cellular measurements. The DeepCell network structure, as illustrated in Figure 3, is composed of an input layer that processes RSS measurements from various cell towers, along with a binary indicator for each tower's activity status. This input undergoes transformation through a multinomial logistic model, which acts as a nonlinear function, generating a probability distribution over virtual grid cells. The model learns to infer the probability distribution of different grid cells by learning the feature vector of training examples. During training, a stochastic gradient descent optimizer minimizes the average cross-entropy distance between the estimated output vector and the one-hot vector. The model utilizes a spatial augmenter module and dropout regularization to enhance robustness. This architecture enables accurate provider-side cellular-based localization. DeepCell, a deep learning-based approach for user location estimation, is described in the online user tracking phase. The system relies solely on the phone ID, specifically the SIM card number, as input. The data collector module retrieves cellular measurements corresponding to the user's phone ID, which are then fed into the grid estimator module. This module uses the trained deep model to estimate the discrete grid cell in which the user is located, given the cellular measurements vector. The grid cell with the maximum probability is selected as the estimated grid cell, denoted by equation 9. To refine the estimated position, the fine estimator module calculates the center of mass of all grid cells, weighted by their respective probabilities, as shown in equation 10. This yields a coarse-grained location estimate of the user. The performance evaluation of DeepCell is discussed, starting with the description of the testbed. The testbed covers a 2.04 square kilometers area in Alexandria, Egypt, with 2013 samples collected by the cellular provider and 42 cell towers in the environment. The data collection process involved wardrivers using GPS-enabled devices to collect GPS ground truth location labels and timestamps. The parameters used in the experiments are summarized in Table 2, including the fingerprint model, grid cell length, number of augmented samples, number of training epochs, learning rate, and cell towers density. The effect of these parameters on DeepCell performance is studied, including the impact of different fingerprint models, grid spacing, number of augmented samples, cell towers density, number of training epochs, and learning rate. Figure 5 shows the effect of different fingerprint models on the system accuracy, with the first model using received signal strength from cell towers only and the second model using RSS with active cells. The performance of DeepCell is evaluated in terms of its accuracy and compared to state-of-the-art techniques. The DeepCell system, a provider-side cellular-based localization system, is evaluated in the paper for its ubiquity and accuracy. The authors investigate various factors impacting localization accuracy, including fingerprint models, grid cell length, augmented samples, cell towers density, training epochs, and learning rate. Figure 5 shows the effect of different fingerprint models on localization accuracy, revealing that incorporating active cells information and spatial augmentation techniques improves accuracy. In Figure 6, the impact of changing grid cell length on localization accuracy is examined, with results indicating that increasing the grid cell length degrades system accuracy, and an optimal value of 100 meters for grid spacing is identified. Figure 7 explores the effect of increasing the number of augmented samples on system accuracy, showing that increasing the number of augmented samples improves accuracy, with DeepCell's performance saturating after approximately 500 samples. The impact of cell towers density on localization accuracy is investigated in Figure 8, revealing that increasing cell towers density leads to better accuracy due to the addition of new features, with DeepCell maintaining its accuracy even with 75% of the typical density. Finally, Figures 9 and 10 evaluate the effect of changing the number of training epochs and learning rate on localization accuracy, respectively. Collectively, these results demonstrate the importance of incorporating active cells information and spatial augmentation techniques to achieve high localization accuracy in the DeepCell system. The performance evaluation of DeepCell, a deep learning-based system for outdoor cellular localization, is presented through various experiments assessing the impact of different parameters on its accuracy. Increasing the number of training epochs leads to better localization accuracy, with increments beyond 400 epochs showing no further improvement. Lowering the learning rate enhances reliability by preventing overshooting during optimization. Compared to the state-of-the-art DeepLock, DeepCell achieves a better localization accuracy by more than 75.4%, highlighting its potential as an ubiquitous accurate localization system. The paper also reviews related work in localization techniques, including GPS-based and sensors-based methods, emphasizing the advantages of DeepCell in terms of energy efficiency, coverage, and accuracy. The paper discusses cellular-based localization techniques, comparing DeepCell with Deep Lock. DeepCell outperforms Deep Lock with a median error of 29 meters, attributed to its ability to capture the joint distribution of input features using a deep model. It leverages the ubiquitous coverage of cellular networks, available on all cell phones, employing a deep model for localization. The paper also discusses deep models-based techniques for fingerprinting, highlighting limitations and the contributions of DeepCell, which addresses these limitations through its virtual gridding approach. The system provides high-accuracy localization for any cell phone, leveraging provider cellular unlabeled data to build the fingerprint radio map and training a deep neural network model. Accurate mobile phone localization is a crucial task, with various approaches employed to achieve it. Three prominent methods are ambience fingerprinting, RSSI fingerprinting, and cellular-based localization. Ambience fingerprinting utilizes the unique ambient radio frequency signals present in each environment to identify a device's location. This method involves creating a radio frequency signature for each location, which is then used to match and localize devices. In RSSI fingerprinting, received signal strength indication values are used to create a fingerprint of the environment, enabling device localization. Cellular-based localization, on the other hand, leverages the signals received from cellular towers to determine a device's location. This method is widely used in commercial applications due to its ease of implementation and low infrastructure costs. However, it suffers from accuracy limitations, particularly in urban canyons and indoor environments. The accuracy of these localization methods heavily relies on the availability of accurate ground truth data for evaluation. Environmental factors such as multipath effects, fading, and interference significantly impact the performance of these systems. To mitigate these effects, researchers have employed machine learning and deep learning techniques to improve localization accuracy. Machine learning algorithms, including nearest neighbors and support vector machines, have been used to classify and localize devices based on their RSSI fingerprints. Deep learning techniques, such as convolutional neural networks, have also been applied to learn complex patterns in ambience fingerprints, enhancing localization accuracy. Future research directions include exploring the use of hybrid approaches that combine multiple localization methods and investigating the impact of 5G networks on mobile phone localization. DeepCell is a provider-side cellular-based localization system that offers ubiquitous and accurate location information. It leverages deep learning models to predict the user's location based on cellular signals, eliminating the need for GPS or Wi-Fi signals. This novel approach, called cellular-based localization, utilizes the cellular network's infrastructure to provide location information. The authors have developed a deep neural network model that can accurately predict the user's location using cellular signal strengths from multiple base stations. This model is trained using a large dataset of cellular signal strengths and their corresponding locations. The system does not require any additional hardware or software on the user's device, making it a low-overhead solution for localization. DeepCell has been tested in various environments and has shown promising results. It outperforms traditional localization methods such as GPS and Wi-Fi-based localization in terms of accuracy and availability. The system is particularly useful in indoor environments where GPS signals are weak or unavailable. However, DeepCell also has limitations. It requires a large dataset of cellular signal strengths and locations for training the model. Additionally, the system's performance may vary depending on the density of cellular base stations in the area. DeepCell has potential applications in various fields such as navigation, location-based services, and public safety. It provides an alternative to traditional localization methods and can be used in conjunction with other technologies to provide more accurate and reliable location information.